Statistics Modeling in Finance, Chapter 4, Inferential Statistics, page 15. Standard deviation conclusion. Standard deviation can be a useful tool for processing numbers and analyzing them. However, it assumes that we are dealing with a normal distribution. A normal distribution results from a random sample of a population. We discussed earlier the difficulties in the sampling process and that it is hard to keep bias from creeping in. It is also necessary to have a sample of sufficient size so that the results are statistically significant. Are samples of real estate sales random? Are they normally distributed? We can't answer that definitively. Probably they are, but not always. If the sample is large enough, it doesn't matter. Let me leave this topic with one startling fact. One sample may be biased or atypical. You just may have happened to pick data that does not represent the population as a whole. If you rely on that one sample, you will produce misleading results. However, if you take several samples and then plot the means of the samples will always form a normal distribution. That's highlighted. So there is always a way to get the truth, no matter how bad the samples are. Instead of relying on one sample of 100, take 10 samples of 10 or 20 observations and plot the means of each data set. That will show a normal distribution. Then you can apply confidence levels and standard deviation analysis. End of page. Page 16, linear regression. Linear regression is another tool we can use to make forecasts or assess probabilities in inferential statistics. An opinion of value is just that, an opinion. It is not a guarantee. And even the word prediction implies a degree of precision that is not there. What we do is more in the way of a forecast. Forecasting, that's highlighted, is defined as to estimate, calculate, or indicate in advance. Forecasts made by appraisers are based on past trends and the perceptions of market participants concerning their continuation or alteration. The meteorologist makes a forecast. We hope we are more accurate than that, but it is similar in concept. The meteorologist studies the available data, applies his or her own analysis, and then makes a forecast. There is an 80% chance of showers this afternoon. Will it happen? Most likely it will. There is an 8 in 10 chance that it will, but there is no guarantee or certainty. There is a strong likelihood. We don't always get it right. Here is another definition. The standard error of forecast, that's highlighted, is defined as an estimate of the variability inherent in a statistical forecast. End of page. Page 17, regression definitions. Back in chapter 1, we looked at data plotted on a scatter diagram, then assessed relationships and trend lines. Regression analysis is defined as a statistical method that examines the relationship between one or more independent variables and a dependent variable. Regression models can be used to examine the structure of a relationship or to forecast dependent variable values. Simple linear regression has one independent variable, whereas multiple linear regression includes more than one independent variable. A dependent variable is defined as the variable being estimated outcome or response variable in a predictive model, such as a multiple linear regression equation. A linear regression is defined as A type of statistical analysis used to investigate a linear relationship between a dependent variable and one or more independent variables used to predict the value of the dependent variable on the basis of the values of the independent variables, and to develop an understanding of how a unit change in an independent variable relates to change in the dependent variable. Linear regression models employing a single independent variable are called simple linear regression models. Those employing more than one independent variable are called multiple linear regression models. Linear regression graphing. Here are 24 cells in a market area, along with the square feet of gross living area for each. Shows the sale price 128,000, GLA 1,115, all the way to 130,000, 1,120 square feet of gross living area. You don't have to do any work this time. I have plotted the prices per square foot on a scatter diagram with the help of Excel. We are trying to demonstrate visually how strong an influence square footage, the independent variable, has on price, the dependent variable. You can see the results on the next page. Page 18, linear regression example number 1. Price per square foot. Okay, let's analyze the chart. Does there appear to be a relationship between square footage and price?
Absolutely. It appears that there's a good, strong relationship between the two variables. The trend of the plot moves up and to the right, and that shows a good correlation.
If you print this chart out on paper, you can take a straight edge and a pencil and draw a trend line that appears to come the closest to all dots. You will be plotting the mean of all observations. You just need to wiggle the ruler around until it looks like you have found one line that minimizes the distance between each dot and the mean. We are striving for a line that has about the same number of dots above the line as below. Go ahead, lay it on there. Let's assume that the trend line you just drew represents the mean of the data set. Even with such an approximate line, we can draw some reasonable conclusions. Number 1, there is strong evidence that as the square footage of the homes increases, the price increases. This is not surprising. Study after study has shown that size is probably the single strongest independent variable to affect price in residential properties. Number 2, can you estimate roughly the amount that the price changes for each square foot change? Look at the graph. Key in on the dots and the trend line between 1,100 square feet and 1,200 square feet. That is where there is the largest concentration of data points. Did you come up with something close to that?
Of course, it's going to vary depending on everybody's individual interpretation and where they drew the trend line. But just for an example, my line, if I start at 1,100 square feet at the bottom and go up until I hit the trend line and then go over to the left, it shows me about 127,000. If I go to 1,200 square feet, go up vertically till I hit the diagonal trend line and then go over to the left edge, that's probably about 138,000. So with my rough figures, the difference between 138,000 and 127 is 11,000 over 100 square feet of difference. Divide 11,000 by 100, and we get $110 for each square foot.
Let's do an estimate. Number 3. If a house sells for $130,000, how many square feet would you expect it to have?
Again, there will be differences, but if I see where my trend line crosses 130,000 and then just drop down a vertical line, I'm looking at something around 1,130 square feet, maybe 1,135, something in that bracket.
Number 4, let's do another estimate. That should be more practical. Use your trend line and eyeball the chart. If a house in that market area has 1,160 square feet, what would you expect the sales price to be?
Here we're going to do a similar type operation. First look along the line at the bottom and find 1160. Then draw a line straight up, a vertical line, and see where it intersects the diagonal trend line. Then just follow across to the left and see where it hits the left axis. I'm showing something around $133,000, maybe $133,500, something in that range. Did you get something pretty close to that?
End of page.